Hi everyone, this is Casey Wolverton with Engineers in Action, and today we're going to be talking about how to identify feasible centerlines by taking the big four considerations into account when you visit a site. So jumping right into it, topography. This is the biggest thing that we need to take into account from a technical perspective when we want to take that initial evaluation of whether a site appears to be feasible or not. So here are the number 4 things that you need to do. Elevation for freeboard, flat spots for the abutments, distance bank to bank is less than 120 meters, and the distance vertically between the banks will be according to a certain value that I'm going to show in this image here. So this image is taken from our Guia Technica, which is a one-page summary of everything you need to do when you visit a site and try and determine if it appears to be feasible. So just taking a look at the image as a whole. So here we have one bank. Here we have the edge of bank. This goes down. This is a gorge with the river flowing through the gorge. Coming up, this is our second edge of bank right here. And then coming back to the right bank here. And so just for clarity, as we're talking, this is the profile as you're looking at the river in profile view. The water is flowing into the page, and so this is the left, this is the right, and we're looking toward downstream. That's what we'll use in all of the following images. So I've marked this up to show where the big four come into play in this image. So first, elevation for freeboard. This is to ensure that we have enough of a distance between the bottom of the decking and the maximum level of the water. And so the important equation here is L over 20. We need the distance between the edge of bank straight down to the maximum level of the water that it ever reaches in a typical flood. Let's say, for example, what is the maximum level of the water? Well, we need this vertical distance to be at least L over 20. Let's go to number 2, flat spots before the abutments. So pretty important, we need somewhere where we can actually construct the abutments. And so here, the important things to take into consideration are that it's less than 20 degrees slope, and that from the edge of the bank backwards away from the river, you have at least 20 meters. And that gives you room to place the abutment and have room for excavations and construction. Number 3, distance, less than 120 meters. So this is the distance from bank to bank horizontally. We need at least 120 meters. And you'll see we do have here a lower limit. It's a little bit more obvious when you're visiting a site. Okay, this is obviously a very small creek. A suspended bridge is probably not necessarily the appropriate intervention here. But 120 meters, this is a little trickier. You'll need to be able to measure that somehow, typically with a rangefinder, because over 120 meters, it gets pretty tricky to do these bridges. We'll talk about that a little bit further on. And so this is our upper limit for bank-to-bank horizontal distance. And finally, bank height difference. So we have edge of bank here on the left, edge of bank here on the right, and the vertical distance between these two needs to be less than L over 25 plus 2. All right. So now that we've discussed that, let's take just a quick look at the structure, just to give you a general idea. So that we're clear, you don't really need to understand too much about these structures in order to determine whether it's feasible, as long as you meet all these requirements on this image. But just so you can sort of visualize while you're there what it's going to look like, here we have, here's our bank, left bank, edge of bank, going down into the gorge. Here's our river, high water level, right bank, edge of bank, and the right bank sloping back. Okay, so what is an abutment? This whole thing is the abutment. We have a foundation here, one tier, the tower, the ramp going back, and the anchor here. And so this is a bridge that has a 25-meter span. This is essentially the smallest span that we offer for this design. And you can see it goes back 9 meters. Some of the things that we can modify here, we can add additional tiers here. So we have only one tier here. We could actually add 2 more tiers for a total of 3 tiers in order to achieve more vertical distance here. So let's say maybe the high water level was higher up. It was up here. And in order to get our freeboard, we need to raise up the tiers. So this is typically the only modification really make, and that adjusts the size of your abutments. But let's take a look here at another example. So you can see this is essentially the same thing, but here we have a 100-meter span. But again, you have one bank here, edge of bank, slopes down. You have the gorge here, your high water level here, and the same thing on this side. And so do note here, instead of the abutments being, I believe they were 9 meters back from the tower on the 25-meter span bridge, here we have 14, right? And with the excavations, you're going to need to bank. You're going to need to bench the excavations for safety reasons, and maybe you need to put some material here, or you need to walk behind here. So this is why we need 20 meters from edge of bank back as a minimum, really, because you've got to have a setback from the bank, you've got to actually have the whole structure, and then you're going to typically need a little bit of room back here. So this is why we need that. Okay, so just to review again, these are big four: elevation for freeboard, flat spots for the abutments, distance bank to bank less than 120 meters, and the vertical height difference as well. Okay, so now I want to run through these scenarios where you're going to come onto site and you're going to say, okay, this clearly is not feasible, right? And so the first situation that we frequently run into is that the site is simply too flat. So here we have, I'm actually going to draw in here a little bit so we can see. I'm going to just not draw the whole bridge, but here we have one tier, let's say one tower, a tier, and a tower. So what is the problem here? The problem here is that how a suspended bridge works. The identifying feature of a suspended bridge is that it sags down like this. All right, so it's sagging down. And then you perhaps can already see the problem here, but we are very, very close to the high water level here. And this isn't ideal because let's say perhaps you have actually the high water level is a little bit higher. What can happen is, well, the whole point of the bridge is so that you don't have to walk through the water. If it's higher than the decking here, the low point of the decking, it's not good because people are still having to walk through the water. Another concern here is that, as you remember, we have the river coming in here. We're looking downstream, water's flowing into the page, right? So it's coming something like this. Let's say you have a tree down here. A really bad storm happens. There's a lot of wind, there's a lot of water. The tree falls into the river. The river's flowing very quickly because there's a storm, it's flooding. And what happens? The tree flows downriver and boom, hits the structure and can potentially cause catastrophic damage to the structure here if it were to really cause damage to the cable itself, but also it could just cause damage to the fencing, make it unsafe for children to cross, for example. Might cause a lot of work. People are going to have to clear the vegetation from the bridge in order for it to be crossable. They're going to have to replace the fencing, most likely. A lot of issues. So this is what we want to avoid, right? So if it's too flat, it doesn't work. What they really need here, and I'll put it in a different color here, let's do yellow, is, let's say we have a tower, and instead of a suspension bridge, or instead of a suspended bridge, I've already given it away, they need a suspension bridge. We, unfortunately, do not build suspension bridges, so somebody else will need to build a bridge there if they really need a bridge at that location, but not feasible because a suspended bridge will not work if it's too flat. Okay, so here's a very quick example. You can see here, this bank is not very tall. We've got maybe 2 meters here. And then same here on this side. And so what will happen is, let's just say, okay, you have your foundation, you have your, let's say this is a tier, this is a tower, it sags down, and here at this spot even, it's pretty long bank to bank. This is a pretty wide river. Actually, what would most likely happen if you were to construct a suspended bridge here is it would hit the ground. So clearly not feasible, doesn't work there. All right, so let's look at another situation. Too steep. All right, this is something we run into quite a bit. And here we have, let's see. So here we have, clearly this is more than 20 degrees from horizontal. And so let's just think through, okay, let's place a tier and a tower here. And actually, if we want to be a little bit more accurate, we've got the ramp, we've got the anchor here. It's going to look something like that. We've got the same thing on this side. You've got your cables are going to come across. So what is the problem here? Perhaps you can already see that in order to build this, we're going to have to dig into the ground here. So we're going to have to excavate all of this, which, that's something we do anyway, except now look at all of this earth that is on top of where you have to excavate. So not only are you going to have to dig down a meter for your foundation and dig down, 2-3 meters to place your anchor, but now you've got all of this hillside on top of it, and this just becomes very quickly a massive amount of earth moving and excavation that needs to be done that doesn't make it feasible to build a bridge in this sort of situation. So what does this look like? So you can see here, let's say, obviously we were able to find a feasible spot at this location, but we went very far upstream, very far downstream, looking for some flat spots where we could actually put the abutments. And so you can see in this sort of topography, it's very steep. So what you really need to do is you would need to, let's go gray here, cut into the mountain here, and we'd put our abutment here, but then you have all of this on top, and you can't just have a huge vertical like this, so you'd need, maybe you're gonna have to bench it like this, and it just ends up being a massive amount of earth that you need to move. So this is why that is not feasible. All right, what is our next situation? Too wide. Okay, so let's go back in our orange. We've got a tier, we've got a tower, we've got a tier and a tower. And so here, we've got room for the abutments, that's good. We've got plenty of freeboard here. We have no fear of the water hitting the bridge, but this distance here horizontally is very large. And so why is this an issue? Okay, well, one problem is that it's very long. You have a lot of tension in the cables. You're going to have to build really massive abutments in order to withstand this force. So that's one thing. It just becomes a lot of rock, a lot of material that you're going to have to build by hand. It's a lot of masonry. But another thing is that you have this surface area of the bridge here. And so you can see, obviously, as the bridge is longer, the surface area increases. And when the bridge is less than 120 meters, you don't really need to account for this surface area. But when it gets this big, something that starts to become a problem is that the wind comes through, right? So let's say wind is this color. Whoa, we've got wind coming through this gorge and hitting this fence. And this is putting a lot of pressure that we have to counteract. And so the mitigation that typically would need to happen here is you need to build a bunch of wind guys coming down and helping to stabilize this force from the wind coming in and hitting the bridge. But this really vastly increases the cost of the bridge. It's a lot more engineering. This is not within our standard designs. So if it's 120 meters, it is not feasible for us to build for those reasons. So here you can kind of see, I'll just mark this up a little bit. So obviously there are some other concerns at this site, only one of which is that this is something like 140 meters away, right? So obviously you've got some pretty extreme slope happening here. This is a very small amount of land. I'm not sure if there's enough room for the abutment, but let's forget about those things for now and recognize that this is pretty far away. And so you'd have to be building wind guys, a huge abutment, all of these things that I discussed earlier that really make it too difficult to build this type of bridge. It doesn't make it feasible for us to build a bridge like this by hand. And so one recommendation I would have is to bring a rangefinder, just a handheld rangefinder with you, because it can be pretty difficult to judge the distance, the difference between 110 meters and 170 meters often is difficult to tell just by eye. And so this is where a rangefinder comes in, incredibly useful, because you can quickly shoot across and say, oh, okay, this is clearly too far away. All right. Another example, and I talked about this early in the beginning, we also have a minimum. And so this is pretty simple. Community members will have trouble crossing, but why don't we build less than 20 meters? The main reason is because you could build a much simpler structure. You could build, let's see, for example here, a simple truss bridge. That would be much more economical, much easier to build. And so we could technically build a suspended bridge here. We just put the abutments a little further back from the bank, but there are better engineering options for this kind of site. A suspended bridge really isn't necessary. You could do a simple bridge across the creek. And here's an example. So you can see here, bank to bank is, I don't know, maybe 5 meters. And so obviously it's too flat here as well, but barring that, this is very, very short. There are better options. All right, and our final example, delta H. This is the vertical height difference between your two edge of banks here. So why won't this work? Well, let's just think through really quickly how the structure works. We have a tier, we have a tower, we have a tier and a tower, and it's going to come up like this. Well, an immediate reason, even if this was structurally sound, this is no longer a bridge. This is a slide, right? And so, especially if it's raining, this is going to be pretty slippery, and this is going to be very difficult to walk up and down. You're going to be walking here. If it's slippery, you're going to be sliding backwards. This really isn't safe. And so this is accounted for here. What is this, +2, you might say? So getting into the design a little bit. So we have a foundation. This is the level of the ground here. We have the foundation. We have 1 tier, 2 tiers, 3 tiers, and the tower, and this is where our cables attach to here as such. This is the maximum amount of tiers that we can have. So the standard, the minimum, is the foundation and 1 tier here, but the maximum is 3. And so we could get, a little bit higher, but after this slope of L/25, it becomes difficult from a serviceability standpoint. It's difficult for people to actually use the bridge if the slope between the two sides is greater than L/25. And it was a little bit hard for me to find in our files actually a good photo of height difference because, let's see over here. You can clearly see the bank here. So you can see here the bank on the other side, clearly taller than the bank on this side. But it was difficult for me to find photos of this because we typically only take photos of sites that we think could potentially be feasible. But you can see here, we've got quite a height difference. Got ... This would come here. This would come here. We've got our 2 handrail cables and our walkway cables coming, something like that. Well, It's a little hard to see with my drawing here, but this is roughly what it would look like, and you just get a lot of slope coming in this direction. All right, so we've walked through all of the big four, what you're looking for when you get to a site, the things you need to take into consideration. And so these are really the main things. Elevation for freeboard. When you know it's not going to work, when it's too flat, right? You need to have a gorge. If you're looking at a floodplain where it's very flat, the cables or the decking are going to be too low, too close to the water, or even in the water, or even not even above the ground because they sag down because this is a suspended bridge. So it can be too flat. The other situation, too steep. We run into this a lot of times. This doesn't work because you have to excavate too much earth. Too wide. This doesn't work because you need huge abutments and you need to mitigate for the wind. And delta H, when you have a really big difference between the two banks, greater than L over 25 plus 2, it doesn't work because it makes the decking too steep and it becomes difficult to walk across. And that's pretty much it. These are the 4 things you need to take into consideration. If you just follow the Guia Technica, you follow these 4 things, you'll be able to identify whether a site is worth studying further. All right, so just very quickly to end it, these are some tools of the trade that I find useful when doing these sort of assessments. So first of all, you need some sort of tool to measure these distances. And so I find a rangefinder to be the most useful. These are handheld, you just point and shoot, and they're not the most exact, so I wouldn't design a bridge off of a rangefinder survey, but it allows you to quickly take shots, pick a center line, see if it appears feasible. If it doesn't, go upstream, try it again, go downstream, try it again. And so when you go to this site, what you're going to have to do is you're going to have to pick a site that very quickly, okay, it looks like this might be feasible. Take these measurements, test it against the big 4, see if it works. If it doesn't, continue going upstream. Typically, I recommend going upstream around 200 meters and going downstream around 200 meters to try and find a spot somewhere along this profile where you can meet all of the requirements of the big 4. A camera, you're going to need to take pictures and videos while you're at your site. Technical survey form, this will be linked, and the Guia Technica, this will be linked as well. These 2 things are things you want to carry with you in the field to help you guide you through the process of seeing whether it's feasible, as well as recording information so that you can get back from the field and see what you're looking at. All right, that's all I have. So for more information, check out our website, eibridges.org. You can see other projects that we have. Currently, we're building in Bolivia and Eswatini, so you can see some more photos, see what these structures look like once they've been constructed, as well as see information about the organization. Thanks.